So let's talk about two very important nucleophilic substitution reactions, specifically the Sn1 and Sn2 mechanisms. Now these are going to become really important because if we're working with Sn1 versus Sn2, it's going to really dictate what happens to the molecule. So the Sn here refers to a substitution of the nucleophilic type. So we have two types of substitution of nucleophilic, 1 and 2. Now the 1 and 2 here are going to refer to the number of things that are involved in terms of making the reaction intermediate. So with an Sn1 reaction, our intermediate is a carbocation. So to basically make our compound, we're going to start with something like CH3Br, and we're going to make a carbocation, and our leading nucleophile is going to go off into space. Now, issues with Sn1, typically you create really high energy carbocations. So something like this would not exist. We couldn't do this by an Sn1 reaction. But if we had a tertiary carbon, so let's say we had a trimethyl carbocation, so CH3 taken 3 times with Br, this might be possible. Now, with the Sn1 mechanism, we create a trigonal planar carbon. We can have our next step in the mechanism, which is the nucleophilic attack, in this case, like a hydroxide attacking it. This Sn1, it can go either side. So if this creates a chiral center, we're gonna get both probably an equal mixture, so we're gonna get a racemic mixture. So if we add an OH minus, it can attack from the front or the back side. And again, if there's any type of stereospecific chemistry, we're gonna see that. What an Sn2 mechanism involves is that we don't go through a carbon cation. What actually we do is we go through a transition state involving both the nucleophile that's coming and whatever compound we're starting with. So if we add in CH3Br and hydroxide, the way we would proceed in terms of this reaction is that the bromine would leave as the hydroxide is coming into the compound. So basically it pushes the bromine off. Now, the upside of this is that we don't ever really go through a carbon cation intermediate, and because we don't go through that, we have less issues of stability. Now, that said, when we do this, what we do see, because it's always an attack on the opposite side of the leading nucleophile, is an inversion of symmetry. So if for whatever reason this is a chiral compound with one configuration or the other, when we do an Sn2 mechanism, we're going to flip it. So if it's L, it's going to go R and vice versa. So this is your big difference here. Sn1 goes through a carbocation that is isolated and an intermediate. Because of that, we basically, if we generate chiral centers by an Sn1 mechanism, we get both forms of the chirality. With Sn2, if we do see an issue with chirality, we end up seeing basically an inversion of the chirality. Now, the other big thing with the Sn1 is that we also can see carbon rearrangement. So we can see hydride and methyl group shifts to try to stabilize this carbocation. This is not going to be true with an Sn2 mechanism. An Sn2 mechanism, because it never really goes through a carbocation, we shouldn't have any issues in terms of molecule rearrangements.